Right now, as you're sitting there, you're existing in a world that's not just what it seems. Atoms, the tiny building blocks of everything around us, are behaving in ways that would make a roller coaster seem tame. Quantum mechanics, the science that tries to make sense of this atomic roller coaster, has revealed a reality that's so strange, it's like a sci-fi movie that's actually real. But here's the kicker. This isn't just some abstract science stuff. It's the foundation of the technology you use every day, from your smartphone to the GPS in your car. So, are you ready to question everything you thought you knew about reality? Let's dive in. The birth of quantum mechanics. Quantum mechanics, the theoretical basis of modern physics, emerged from the need to explain phenomena that classical physics could not. At the turn of the 20th century, scientists like Max Planck and Albert Einstein introduced the idea that energy is quantized, meaning it comes in discrete packets called quanta. This was a radical departure from the continuous waves described by classical physics. Planck's work on black-body radiation and Einstein's explanation of the photoelectric effect laid the groundwork for what would become quantum mechanics. These early insights challenged the deterministic view of the universe, suggesting instead that nature is fundamentally probabilistic. The birth of quantum mechanics also brought with it a host of interpretations that sought to make sense of its counterintuitive predictions. The Copenhagen interpretation, championed by Niels Bohr and Werner Heisenberg, posits that a quantum system remains in a superposition of states until it is measured. This interpretation introduces the concept of wave function collapse, where the act of observation forces the system to choose a definite state. However, this raises profound questions about the nature of reality. If observation affects the outcome, what does that say about the independence of the physical world from the observer? These questions blur the lines between physics and philosophy, inviting us to reconsider our understanding of reality. In daily life, quantum mechanics might seem abstract and distant, but its principles are increasingly finding practical applications. Quantum computing, for instance, leverages the principles of superposition and entanglement to perform calculations that would be impossible for classical computers. This technology has the potential to revolutionize fields like cryptography, drug discovery, and artificial intelligence. Moreover, quantum mechanics underpins technologies we use every day, from lasers to MRI machines. The dual nature of light, both particle and wave, is harnessed in fiber optic communication, enabling the high-speed internet that connects us globally. These applications show that quantum mechanics is not just a theoretical curiosity, but a foundational framework that shapes our modern world. The interpretations of quantum mechanics continue to evolve, with new theories like the many-worlds interpretation and objective collapse models offering alternative explanations. The many-worlds interpretation suggests that all possible outcomes of quantum measurements become real in some world or universe. This idea, while fascinating, raises questions about the nature of reality and the multiverse. Objective collapse models, on the other hand, propose that the wave function collapses spontaneously without the need for an observer. These interpretations challenge our understanding of the universe and invite us to explore the deeper implications of quantum theory. As we delve deeper into the quantum realm, we are forced to confront the limits of our knowledge and the mysteries that still lie ahead. Classical mechanics versus quantum mechanics. Classical mechanics, the physics of the everyday world, deals with objects larger than atoms and moving slower than the speed of light. It's the realm of billiard balls, planets, and baseballs. Here, objects have well-defined positions and velocities. If you know the initial conditions and the forces acting on an object, you can predict its future behavior with certainty. This is the world of Isaac Newton, where cause and effect rule the day. It's intuitive, predictable, and makes sense to our everyday experiences. When you kick a soccer ball, you expect it to follow a certain trajectory, and it does, every time. This is the power and simplicity of classical mechanics. Quantum mechanics, on the other hand, is the physics of the very small. It governs the behavior of particles like electrons and photons, objects smaller than atoms. In this realm, objects don't have well-defined positions and velocities. Instead, they exist in a state of probability, described by a wave function. This is the world of Schrödinger's cat, both alive and dead until observed. It's counterintuitive, probabilistic, and often seems to defy common sense. If you could shrink down and kick a quantum soccer ball, it might go left, right, or even backwards, all at the same time, until you observe it. This is the strange and fascinating world of quantum mechanics. The difference between these two realms is stark. In classical mechanics, objects have definite properties. In quantum mechanics, they don't. In classical mechanics, measurements don't affect the system. In quantum mechanics, they do. This leads to different interpretations of what's really going on. Some physicists, like Niels Bohr, argued that quantum mechanics is just a tool for making predictions, and we shouldn't try to interpret it too literally. Others, like Erwin Schrödinger, believe that the wave function is a real, physical entity. Still others, like Hugh Everett, propose that all possible outcomes of quantum measurements actually happen in a constantly splitting universe. These interpretations raise profound questions about the nature of reality. Is the universe fundamentally probabilistic? Does consciousness play a role in shaping reality? These are the kinds of questions that quantum mechanics forces us to confront. So, how does this affect our daily lives? Well, quantum mechanics might seem abstract and removed from our everyday experiences, but it's actually all around us. It's in the semiconductors that power our computers and smartphones. It's in the lasers that scan our groceries and play our music. It's even in the MRI machines that diagnose our injuries and illnesses. Quantum mechanics might be strange, but it's also incredibly useful. It's a testament to the power of human curiosity and ingenuity, pushing us to explore the boundaries of reality and harness its secrets for our benefit. Wave-particle duality. In the realm of quantum mechanics, wave-particle duality stands as a fundamental concept that challenges our classical intuitions about the nature of reality. At the heart of this phenomenon lies the idea that particles, such as electrons or photons, can exhibit both wave-like and particle-like properties. This duality is not a matter of either-or, but rather a fundamental aspect of quantum objects. For instance, in the famous double-slit experiment, particles like electrons are fired one at a time through two slits. When observed, they create an interference pattern characteristic of waves, yet they also behave as discrete particles, appearing as distinct dots on a detector screen. This dual nature defies classical physics and suggests that quantum objects exist in a superposition of states until measured. Interpreting wave-particle duality has led to a variety of theoretical frameworks, each offering a different perspective on the nature of reality. The Copenhagen interpretation, one of the most widely accepted, posits that particles do not have definite properties until they are measured. In this view, the act of measurement collapses the wave function, forcing the particle to choose a definite state. This interpretation raises profound questions about the role of the observer in quantum mechanics. If consciousness plays a part in determining reality, what does that say about the nature of the universe? Alternatively, the many-worlds interpretation suggests that all possible outcomes of quantum measurements become real in some world or universe. This multiverse idea implies that every quantum event branches reality into a multitude of parallel universes, each representing a different outcome. Such interpretations push the boundaries of our understanding and invite speculation about the fabric of existence. Connecting wave-particle duality to daily life might seem challenging, but its implications are far-reaching. Quantum technologies, such as lasers and magnetic resonance imaging (MRI), rely on the principles of wave-particle duality. Lasers, for example, exploit the wave-like properties of photons to produce coherent light, which is used in everything from telecommunications to surgical procedures. MRI machines use the spin of protons in the presence of a magnetic field to create detailed images of the human body. These technologies highlight how quantum mechanics, once a realm of abstract theory, now underpins much of modern life. Moreover, the study of wave-particle duality has inspired new ways of thinking about information and computation. Quantum computing, which leverages the superposition and entanglement of quantum bits, qubits, promises to revolutionize fields like cryptography and optimization. As researchers delve deeper into the quantum world, the boundaries between theory and application continue to blur, offering glimpses into a future where the strange and the practical intertwine. The double-slit experiment. Light behaves as both a wave and a particle. This wave-particle duality is one of the most mind-bending aspects of quantum mechanics. The double-slit experiment is a classic demonstration of this phenomenon. In this experiment, particles like electrons or photons are fired at a barrier with two slits. When observed, they create an interference pattern on a detector screen behind the barrier, as if they were waves passing through both slits simultaneously. However, if you try to observe which slit each particle goes through, the interference pattern disappears, and the particles behave like discrete particles, not waves. This suggests that the act of observation affects the behavior of the particles. It's as if the particles are waiting to see how they're being watched before deciding how to behave. This is not just a quirk of light or electrons. It's a fundamental aspect of quantum mechanics that applies to all particles, including the ones that make up you and me. The double-slit experiment has led to various interpretations of quantum mechanics. One is the Copenhagen interpretation, which suggests that particles don't have definite properties until they are measured. Another is the many worlds interpretation, which proposes that all possible outcomes of quantum measurements become real in some world or universe. There's also the pilot wave theory, which suggests that particles have definite properties and are guided by a pilot wave. Each interpretation has its strengths and weaknesses, and none has been proven definitively correct. This leaves room for ongoing debate and exploration. It's like trying to understand a dream. Different people might have different interpretations, and none might be entirely satisfying. The implications of the double-slit experiment extend beyond the lab and into our daily lives. For instance, it challenges our classical intuition about how the world works. In our everyday experience, things seem to have definite properties independent of observation. But quantum mechanics suggests that this might not be the case at the fundamental level. This can lead to some profound questions. If observation affects the behavior of particles, does consciousness play a role in shaping reality? If particles can exist in multiple states at once, what does that mean for our understanding of free will? These are not just abstract philosophical questions. They have practical implications for technologies like quantum computing and cryptography. It's like realizing that the rules of the game you've been playing all your life might be different than you thought. How would you change your strategy if you knew that your choices could affect the very nature of the game itself? Moreover, the double-slit experiment reminds us of the interconnectedness of all things. In the quantum world, particles can become entangled, meaning the state of one can instantly affect the state of another, no matter the distance between them. This is what Einstein famously referred to as spooky action at a distance. It's as if the universe is a vast, interconnected web, and everything is somehow connected to everything else. This interconnectedness is not just a theoretical concept. It's been demonstrated in experiments and is the basis for technologies like quantum teleportation. So, the next time you're feeling disconnected or isolated, remember that at the fundamental level, you're part of a vast, interconnected quantum web. It's a humbling and awe-inspiring thought, don't you think? Quantum superposition. Quantum superposition is a fundamental principle of quantum mechanics that defies classical intuition. At its core, it posits that a quantum system can exist in multiple states simultaneously until it is measured. This is often exemplified by the thought experiment of Schrödinger's cat, which is simultaneously both alive and dead due to being linked to a quantum event. In reality, this principle is observed in particles like electrons, which can spin in multiple directions at once. This property is not just a theoretical curiosity. It's the backbone of technologies like quantum computers and MRI machines. Yet, it raises profound questions about the nature of reality. If particles can be in multiple states at once, what does that say about the deterministic world we perceive? The interpretations of quantum superposition vary widely. The Copenhagen interpretation, one of the most widely accepted, suggests that a quantum system remains in superposition until it is measured, at which point it collapses into a definite state. This raises the question, what constitutes a measurement? Is it the interaction with a conscious observer, or is it a more fundamental process? The many worlds interpretation takes a different approach, proposing that all possible outcomes of a quantum measurement become real in some world or universe. This leads to a multiverse where every quantum possibility is realized. These interpretations challenge our understanding of reality and perception. How do we reconcile the probabilistic nature of quantum mechanics with the seemingly solid and predictable world we experience daily? Quantum superposition has practical implications that are increasingly relevant in our daily lives. Quantum computers, for instance, leverage superposition to perform complex calculations much faster than classical computers. This could revolutionize fields like cryptography, drug discovery, and artificial intelligence. Similarly, quantum sensors exploit superposition to achieve unprecedented levels of precision, potentially improving medical imaging and navigation systems. Yet, the strange nature of superposition also raises ethical and philosophical questions. If particles can be in multiple states, what does that imply about the nature of choice and free will? Does it suggest a more interconnected and holistic universe than we previously thought? These questions bridge the gap between abstract science and profound existential inquiries, inviting us to reconsider our place in the cosmos. Schrödinger's cat. Quantum mechanics, the branch of physics dealing with the smallest particles in the universe, has consistently challenged our understanding of reality. At the heart of this challenge lies Schrödinger's cat, a thought experiment devised by Austrian physicist Erwin Schrödinger. This paradox illustrates the peculiar nature of quantum superposition, where a system can exist in multiple states simultaneously until measured. In the experiment, a cat is placed in a sealed box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the Geiger counter triggers the vial to break, releasing the poison and killing the cat. However, until the box is opened and observed, the cat is simultaneously both alive and dead, a superposition of states. This thought experiment isn't just a quirky tale. It's a profound illustration of the counterintuitive nature of quantum mechanics. In our daily lives, we're accustomed to things being in one state or another. A light is either on or off. A switch is either up or down. But in the quantum world, particles can exist in multiple states at once. This principle is what allows technologies like quantum computers to perform complex calculations much faster than classical computers. It's also why scientists are exploring quantum cryptography for ultra-secure communication. The implications are vast, touching everything from medical imaging to artificial intelligence. Interpreting Schrödinger's cat has led to various philosophical debates and scientific interpretations. The Copenhagen interpretation, one of the most widely accepted, suggests that the cat is in a superposition of states until observed. This implies that consciousness plays a role in determining reality. Other interpretations, like the many-worlds interpretation, propose that all possible outcomes of quantum measurements become real in some world or universe. This raises intriguing questions about the nature of reality and our place in it. For instance, if every quantum decision branches into a new universe, how many versions of you are there right now? It's a mind-bending idea, but one that some physicists take seriously. The implications of Schrödinger's cat extend beyond the lab and into our everyday lives. Quantum mechanics influences the technology we use daily, from the GPS on our phones to the MRI machines in hospitals. Understanding these principles can help us appreciate the intricate dance of particles that underpins our reality. It also encourages us to question our assumptions about the world. Just as the cat is both alive and dead until observed, perhaps our perceptions shape reality in ways we're only beginning to understand. This thought experiment reminds us that the universe is far stranger and more wonderful than we might imagine. It invites us to embrace uncertainty and wonder, qualities that are as valuable in science as they are in life. The measurement problem. Quantum mechanics, the branch of physics dealing with the smallest particles in the universe, has consistently challenged our understanding of reality. At the heart of this challenge lies the measurement problem, a puzzle that arises when quantum systems interact with measurement devices. In the quantum world, particles don't have definite properties until they are measured. For instance, an electron doesn't have a specific location or momentum until we observe it. This is encapsulated in the wave function, a mathematical description that contains all possible states of a quantum system. The measurement problem questions what happens to the wave function when a measurement is made. Does it collapse to a single state, or does something else occur? Several interpretations attempt to address this conundrum. The Copenhagen interpretation, one of the most widely accepted, suggests that the wave function collapses upon measurement, and the system transitions to a definite state. However, this raises questions about the role of the observer. If consciousness causes collapse, what does that imply about reality? Other interpretations, like the many worlds interpretation, propose that all possible outcomes of a quantum measurement become real in some world or universe. This leads to a multiverse where every quantum possibility is realized. Yet another approach, the pilot wave theory, posits that particles have definite positions and are guided by a pilot wave, avoiding the collapse of the wave function altogether. These interpretations not only challenge our scientific understanding, but also invite us to reflect on our daily experiences. Consider the act of making a decision. In classical physics, choices are clear-cut, but in quantum terms, they might resemble superpositions of possibilities until observed. This analogy, while not perfect, encourages us to think about the fluidity of reality. Moreover, the measurement problem highlights the interconnectedness of the observer and the observed. In everyday life, our perceptions shape our reality, much like how measurements shape quantum systems. This raises open-ended questions. How much of our reality is shaped by our observations? Can we ever truly separate ourselves from the systems we observe? The measurement problem also has practical implications. Quantum technologies, such as quantum computers and quantum cryptography, rely on the principles of quantum mechanics. Understanding the measurement problem is crucial for advancing these technologies. For example, quantum computers use quantum bits or qubits, which can be in a superposition of states. Measuring these qubits collapses their states, which is both a challenge and an opportunity. In quantum cryptography, the no-cloning theorem and the principles of quantum measurement ensure secure communication. These applications show that the measurement problem is not just a philosophical puzzle, but a practical consideration in modern technology. As we continue to explore the quantum world, the measurement problem will remain a central theme, inviting us to question and redefine our understanding of reality. Copenhagen interpretation. Quantum mechanics, the branch of physics dealing with the smallest particles in the universe, has always been a realm of mystery and fascination. At the heart of this enigma lies the Copenhagen interpretation, a framework that attempts to make sense of the peculiar behavior of quantum particles. Developed by Niels Bohr and Werner Heisenberg, this interpretation suggests that a quantum system remains in a superposition of all possible states until it is measured. It's like saying a spinning coin is neither heads nor tails until it lands and you look at it. This idea challenges our everyday experiences, where objects seem to have definite states regardless of observation. Yet, in the quantum world, observation itself alters the state of the system, a concept known as wave function collapse. This raises profound questions about the nature of reality. Is reality fundamentally probabilistic, or is there a deeper, hidden order that we're yet to uncover? The Copenhagen interpretation also introduces the concept of complementarity, which posits that particles can exhibit both wave-like and particle-like properties, but not simultaneously. This is akin to a chameleon changing its colors to blend into different environments. For instance, in the famous double-slit experiment, particles of light, or photons, create an interference pattern characteristic of waves when not observed. However, when observed, they behave like discrete particles, landing on specific points. This duality is a cornerstone of quantum mechanics and has practical implications in technologies like electron microscopes and quantum computing. It's a reminder that the universe doesn't always adhere to our intuitive notions of how things should behave. Moreover, the interpretation brings up the observer effect, a principle stating that the act of measurement inevitably disturbs the system being observed. This is not just a theoretical quirk, but has real-world implications. In quantum cryptography, for example, any attempt to eavesdrop on a quantum communication channel would inevitably alter the system, alerting the communicating parties to the presence of an intruder. This makes quantum cryptography potentially unbreakable. Yet, the role of the observer in quantum mechanics is still a topic of debate. Is the observer a conscious being, or is it any interaction that causes the wave function to collapse? This ambiguity opens up a can of worms about the nature of consciousness and its role in the physical world. The Copenhagen interpretation, while widely accepted, is not without its critics and alternatives. Some physicists argue that it's incomplete or even inconsistent. Interpretations like many-worlds or pilot wave theory offer different takes on quantum mechanics, each with its own implications for the nature of reality. These debates are not just academic exercises. They have practical consequences. Our understanding of quantum mechanics influences how we develop new technologies, from quantum computers to advanced medical imaging. It also shapes our philosophical views on the universe and our place in it. So, the next time you're using a GPS or a smartphone, remember that the quantum world is not just a realm of abstract theories, but a fundamental part of your daily life. Many worlds interpretation. Quantum mechanics, the branch of physics dealing with the smallest particles in the universe, has always been a realm of mind-bending ideas. One of the most fascinating interpretations within this field is the many-worlds interpretation, MWI. Proposed by Hugh Everett III in the mid-20th century, MWI suggests that all possible outcomes of quantum measurements become real in some world or universe. This means that for every decision you make, the universe splits and every possible outcome manifests in a separate, branching reality. It's a bit like a cosmic choose-your-own-adventure story, where every choice leads to a new, parallel world. In our daily lives, we experience a single, linear reality. We make choices, face consequences, and move forward. But according to MWI, there are countless versions of you living out every possible version of your life. For instance, if you're deciding whether to have coffee or tea in the morning, MWI posits that there's a universe where you chose coffee and another where you chose tea. This idea can be both thrilling and unsettling. It challenges our conventional understanding of reality and forces us to consider the multitude of possibilities that exist beyond our immediate perception. It's like standing at a crossroads, knowing that every path you take leads to a different version of yourself. The many-worlds interpretation also raises intriguing questions about identity and consciousness. If there are infinite versions of you, each making different choices, what does that mean for your sense of self? Are you the sum of all your possible selves, or just one version among many? These questions don't have easy answers, but they invite us to think deeply about the nature of existence. They also connect to broader philosophical debates about free will and determinism. If every possible outcome is realized in some universe, does that mean our choices are predetermined, or do we still have agency within our own reality? It's a complex puzzle that blurs the lines between science and philosophy. Moreover, MWI has practical implications for our understanding of quantum mechanics. It eliminates the need for wave function collapse, a controversial aspect of other interpretations like the Copenhagen interpretation. In MWI, the wave function never collapses. It simply branches into multiple, non-communicating worlds. This makes MWI a more deterministic and less mysterious interpretation of quantum mechanics. However, it also introduces its own set of challenges, such as the problem of defining what constitutes a world and how these worlds interact, if at all. Despite these challenges, MWI remains a compelling and widely discussed interpretation, offering a unique perspective on the nature of reality. It's a reminder that the universe is far stranger and more complex than it appears, and that our understanding of it is always evolving. Pilot wave theory. Pilot wave theory, also known as Bohmian mechanics, offers a deterministic interpretation of quantum mechanics. It posits that particles have definite positions and trajectories, guided by a pilot wave that evolves according to the Schrödinger equation. This wave function doesn't represent a probability distribution, but rather a real, physical field that directs the motion of particles. In this view, quantum randomness is an illusion, a result of our ignorance about the initial conditions of the pilot wave. It's a bit like watching a dance where you can see the dancers, but not the music guiding their steps. You might think their movements are random, but they're actually following a complex, invisible rhythm. This interpretation raises intriguing questions about the nature of reality. If the pilot wave is real, then the universe is deterministic, and quantum indeterminacy is a consequence of our limited knowledge. But what does this mean for our everyday lives? If every quantum event is predetermined, does that imply our choices are as well? It's a slippery slope, but not necessarily a bleak one. Think of it like a river. The water flows in a certain direction, but the path it takes is influenced by countless factors, from the shape of the riverbed to the leaves floating on its surface. In this analogy, the river is the pilot wave, and the leaves are our choices. We might not have free will in the absolute sense, but our actions still have real, meaningful consequences. Pilot wave theory also challenges our understanding of nonlocality in quantum mechanics. In the famous Einstein-Podolsky-Rosen paradox, two particles can become entangled, meaning the state of one instantly influences the state of the other, no matter the distance between them. In the pilot wave interpretation, this isn't a spooky action at a distance, but a natural consequence of the particles being guided by the same underlying wave function. It's like two dancers performing a synchronized routine. They might be far apart on the stage, but they're following the same music, the same rhythm. This interpretation doesn't make non-locality any less strange, but it does provide a framework for understanding it. However, pilot wave theory isn't without its challenges. For instance, it requires the wave function to have an infinite number of hidden variables to account for all possible particle positions. Moreover, it's not clear how these hidden variables interact with the physical world. Despite these issues, the theory offers a compelling alternative to the more widely accepted Copenhagen interpretation. It invites us to question our assumptions about reality and consider that there might be more to the universe than meets the eye. After all, just because we can't see the music doesn't mean it isn't there, guiding the dance of the cosmos. Quantum decoherence. Quantum decoherence is a process that describes how quantum systems interact with their environment, leading to the loss of quantum coherence. This phenomenon is crucial for understanding how classical reality emerges from the strange rules of quantum mechanics. At the quantum level, particles can exist in multiple states simultaneously, a property known as superposition. However, when these particles interact with their surroundings, they quickly lose this quantum behavior and start acting in a more classical manner. This transition is what we observe in our everyday world, where objects don't seem to be in multiple places at once or tunnel through walls. The environment causes quantum systems to decohere by entangling with them, effectively measuring the system and collapsing its quantum state into a definite classical state. For instance, a particle in a superposition of states might interact with a photon, which then carries information about the particle's state away. This interaction causes the particle's quantum state to become entangled with the photon, and the particle's state appears to collapse into a single, definite state. This process is why we don't see quantum superpositions in our daily lives. A cat in a box isn't both alive and dead because the box and its contents are constantly interacting with the environment, causing decoherence. Interpretations of quantum mechanics vary widely when it comes to decoherence. Some, like the Copenhagen interpretation, suggest that decoherence explains why we don't observe quantum superpositions macroscopically. Others, like many-worlds interpretation, propose that decoherence is what causes the universe to split into multiple branches, each representing a different outcome of a quantum measurement. Decoherence theory also raises intriguing questions. If the environment is responsible for collapsing the quantum state, what constitutes the environment? Is it truly objective, or does it depend on the observer's perspective? These questions blur the line between the quantum and classical worlds, challenging our understanding of reality. In daily life, quantum decoherence might seem abstract, but it has practical implications. For example, quantum computers rely on maintaining quantum coherence to perform calculations. Decoherence is a significant challenge for these machines, as any interaction with the environment can cause errors. Scientists are working on ways to isolate quantum systems to minimize decoherence, a field known as quantum error correction. Understanding decoherence also helps in developing technologies like quantum cryptography, which promises ultra-secure communication. Moreover, it makes us ponder the nature of reality. If our everyday world is a result of decoherence, what does that say about the underlying quantum reality? Is our classical experience just a simplified version of a more complex quantum world? These questions invite us to think deeply about the fabric of existence. Entanglement and non-locality. Quantum entanglement is a phenomenon where two or more particles become inextricably linked, such that the state of one particle instantaneously influences the state of the other, no matter the distance separating them. This spooky action at a distance, as Einstein famously called it, defies classical intuition and has been experimentally verified numerous times. For instance, measuring the spin of one electron in an entangled pair immediately determines the spin of the other, even if it's light years away. Nonlocality, closely tied to entanglement, refers to the idea that objects can be instantaneously connected, regardless of the spatial separation between them. This challenges our everyday notions of locality and causality, where effects are thought to propagate at finite speeds, typically the speed of light. Interpreting entanglement and non-locality has sparked fierce debates among physicists and philosophers alike. The Copenhagen interpretation, one of the earliest, suggests that particles don't have definite properties until they are measured. In this view, entanglement is a fundamental feature of quantum mechanics, and non-locality is a consequence of the measurement process. On the other hand, the many-worlds interpretation posits that all possible outcomes of quantum measurements become real in some world or universe. Here, entanglement and non-locality are manifestations of the branching of universes. Then there's the pilot wave theory, which proposes that particles have definite trajectories guided by a pilot wave, making entanglement and non-locality less mysterious but more complex. Each interpretation raises profound questions. If particles can be instantaneously connected, does this imply a deeper, hidden structure to reality? Could entanglement be harnessed for faster-than-light communication, or does it merely reflect the limits of our classical understanding? In daily life, quantum entanglement might seem abstract and disconnected, but its implications are far-reaching. Quantum computing, for example, relies on entangled qubits to perform complex calculations much faster than classical computers. Entanglement is also being explored for secure communication through quantum cryptography, where any eavesdropping attempt would disturb the entangled states and be immediately detected. Moreover, entanglement and non-locality challenge our fundamental understanding of reality, prompting us to question the nature of space, time, and causality. They suggest that the universe might be far more interconnected and mysterious than we ever imagined. This raises intriguing questions about the fabric of reality itself. Could the universe be a vast, entangled web of connections? How does consciousness fit into this quantum tapestry? These are the kinds of open-ended questions that keep scientists and philosophers up at night, driving the quest for a deeper understanding of the nature of reality. Bell's theorem. Bell's theorem, formulated by physicist John Stuart Bell, is a fundamental result in quantum mechanics that addresses the nature of reality and the limitations of classical physics. At its core, the theorem provides a way to test the hidden variable theories that aim to explain quantum mechanics in terms of underlying, classical-like variables. These theories suggest that quantum particles have definite properties before they are measured, contrary to the probabilistic nature of quantum mechanics. Bell's theorem, however, shows that no physical theory of local hidden variables can ever reproduce all the predictions of quantum mechanics. The theorem is based on the idea of entanglement, a phenomenon where two or more particles become correlated in such a way that the state of one particle instantly influences the state of the other, no matter the distance between them. This non-locality is a cornerstone of quantum mechanics and is what Einstein famously referred to as spooky action at a distance. Bell's theorem provides a way to quantify this non-locality and test it experimentally. The most famous experiments, such as those conducted by Alain Aspect in the 1980s, have consistently shown that quantum mechanics violates the inequalities derived from Bell's theorem, thereby ruling out local hidden variable theories. Interpretations of Bell's theorem and its implications vary widely. Some physicists argue that it supports the idea that reality is inherently non-local, meaning that particles can influence each other instantaneously across vast distances. Others suggest that it points to a more fundamental level of reality that we have not yet discovered. The theorem also raises profound questions about the nature of causality and determinism. In everyday life, we often assume that events have clear causes and that the future is determined by the present. But quantum mechanics, as revealed by Bell's theorem, challenges these assumptions, suggesting a more probabilistic and interconnected universe. The practical implications of Bell's theorem are also significant. Quantum entanglement, for instance, is a resource for quantum computing and quantum cryptography. These technologies rely on the non-local correlations predicted by quantum mechanics to perform calculations and secure communications in ways that are impossible with classical systems. As our understanding of quantum mechanics deepens, so too does our ability to harness its strange and counterintuitive features for practical applications. Yet, the philosophical implications remain as intriguing as ever. How do we reconcile the deterministic world we experience daily with the probabilistic, non-local world revealed by quantum mechanics? This question continues to fuel debates and research, pushing the boundaries of our understanding of reality. Quantum information. Quantum information is a fascinating field that merges quantum mechanics with information theory, exploring how data is stored, processed, and transmitted at the quantum level. At its core, quantum information relies on the principles of superposition and entanglement. Superposition allows quantum bits, or qubits, to exist in multiple states simultaneously, unlike classical bits that are strictly 0 or 1. Entanglement, on the other hand, links qubits in such a way that the state of one directly influences the state of another, no matter the distance between them. These phenomena open up possibilities for quantum computing, cryptography, and communication that are fundamentally different from classical approaches. The nature of reality takes on an intriguing twist when viewed through the lens of quantum information. For instance, quantum teleportation doesn't involve moving matter, but rather transferring the quantum state of a particle from one location to another using entanglement and classical communication. This process doesn't violate the speed of light because the classical information transfer is still bound by relativistic constraints. It's a bit like sending a detailed map of a treasure's location instead of the treasure itself. Such concepts challenge our everyday notions of information transfer and reality, making us question the very fabric of how we understand and interact with the world. Interpretations of quantum mechanics add another layer of complexity to the discussion. The Copenhagen interpretation, one of the most widely accepted, suggests that a quantum system remains in superposition until it is measured, at which point it collapses into a definite state. This raises profound questions about the role of the observer in shaping reality. Other interpretations, like the many-worlds interpretation, propose that all possible outcomes of quantum measurements actually occur, each in a separate, branching universe. These ideas might seem far removed from daily life, but they have practical implications for technologies like quantum computers, which could solve problems intractable for classical computers. Quantum information also has the potential to revolutionize everyday technologies. Quantum cryptography, for example, uses the principles of quantum mechanics to create virtually unbreakable encryption. Any attempt to eavesdrop on a quantum encrypted message would disturb the quantum states, alerting the communicators to the presence of an intruder. This could make online transactions, secure communications, and data storage infinitely more secure. Similarly, quantum sensors could enhance medical imaging, navigation systems, and environmental monitoring, providing unprecedented levels of accuracy and sensitivity. The integration of quantum information into daily life is still in its infancy, but the potential is vast and exciting. Quantum computing. Quantum computing is a rapidly evolving field that leverages the principles of quantum mechanics to process information in ways that classical computers cannot. At its core, quantum computing uses quantum bits, or qubits, which can exist in multiple states simultaneously thanks to a property called superposition. This is a stark contrast to classical bits, which can only be in a state of 0 or 1. Additionally, qubits can be entangled, meaning the state of one qubit can be directly related to the state of another, even over large distances. This entanglement allows for complex calculations to be performed much more efficiently. For instance, a quantum computer could potentially factor large numbers exponentially faster than classical computers, which has significant implications for cryptography. The nature of reality in quantum mechanics is deeply interconnected with the principles that underpin quantum computing. One of the most intriguing interpretations is the Copenhagen interpretation, which suggests that a quantum system remains in superposition until it is measured. This raises profound questions about the role of the observer in determining reality. Another interpretation, the many-worlds interpretation, posits that all possible outcomes of quantum measurements are realized in some world or universe. These interpretations challenge our classical notions of reality and perception. For example, If you were to perform a quantum computation according to the many worlds interpretation, every possible result of that computation would exist in a separate, branching universe. This idea, while mind-bending, has sparked countless debates and explorations into the fundamental nature of existence. Quantum computing also has practical implications that could revolutionize various aspects of daily life. For instance, quantum computers could significantly enhance drug discovery by simulating molecular interactions with unprecedented accuracy. This could lead to the development of new medications and treatments much more quickly than current methods allow. Additionally, quantum computing could optimize complex systems, such as traffic flow in cities or supply chain management, leading to more efficient and sustainable practices. However, the path to widespread quantum computing adoption is fraught with challenges. One of the biggest hurdles is maintaining the stability of qubits, as they are highly susceptible to environmental noise and decoherence. Researchers are actively working on developing error correction techniques and more stable qubit designs to overcome these issues. The potential of quantum computing extends beyond practical applications and delves into philosophical and ethical questions. For example, if quantum computers can solve problems that are currently intractable, what does that mean for fields like artificial intelligence and machine learning? Could quantum computers lead to the development of highly advanced AI systems that surpass human intelligence? These are open-ended questions that invite speculation and debate. Moreover, the ethical implications of quantum computing are vast. For instance, the ability to break classical encryption methods could have profound implications for cybersecurity and privacy. It raises questions about how societies can adapt to and regulate these powerful technologies. As quantum computing continues to evolve, it will be crucial to consider not just the technical advancements, but also the broader impact on society and our understanding of reality. Quantum cryptography. Quantum cryptography is a cutting-edge field that leverages the principles of quantum mechanics to secure communication. At its core, it uses the behavior of quantum particles, such as photons, to encode and transmit information in a way that is inherently secure. One of the most promising applications is quantum key distribution, QKD, which allows two parties to generate a shared, secret key that can be used for encryption and decryption. The security of QKD relies on the fundamental laws of physics, making it theoretically immune to any computational attacks, including those from quantum computers. The nature of reality in quantum mechanics is deeply intertwined with the principles that underpin quantum cryptography. Quantum superposition and entanglement are two key phenomena that play a crucial role. Superposition allows particles to exist in multiple states simultaneously, while entanglement creates a strong correlation between particles such that the state of one instantly influences the state of another, regardless of distance. These properties enable the creation of secure communication channels where any attempt to eavesdrop would disturb the system and be immediately detectable. This raises intriguing questions about the nature of reality itself. If particles can be entangled and influence each other instantaneously, what does this mean for our understanding of space and time? How does this challenge our classical notions of causality and locality? In practical terms, quantum cryptography is already being implemented in various real-world scenarios. For instance, banks and government agencies are exploring its use to protect sensitive data. The Chinese satellite Mischius, launched in 2016, demonstrated the feasibility of QKD over long distances, including intercontinental communication. However, the technology is not without its challenges. The need for specialized equipment and the sensitivity of quantum systems to environmental noise make widespread adoption difficult. Yet, the potential benefits are immense. As quantum computing advances, traditional encryption methods may become obsolete, making quantum cryptography a vital tool for future security. The philosophical implications of quantum mechanics and its applications in cryptography are profound. They challenge our everyday understanding of the world and force us to reconsider the boundaries of what is possible. For example, the idea that information can be transmitted securely based on the laws of physics rather than mathematical complexity is a paradigm shift. It also raises ethical questions. If quantum cryptography becomes ubiquitous, how will it affect privacy and surveillance? Will it create new forms of digital inequality? These are open-ended questions that require careful consideration as the technology evolves. The intersection of quantum mechanics and daily life is becoming increasingly relevant, and the implications are far-reaching. The nature of reality. Quantum mechanics has profoundly challenged our understanding of reality, revealing a world that is far stranger and more counterintuitive than classical physics could have predicted. At the heart of this puzzle is the wave function, a mathematical description of the state of a quantum system. This function doesn't provide definite values for properties like position or momentum, but rather gives probabilities. This inherent uncertainty is not a reflection of our lack of knowledge, but a fundamental aspect of nature. Schrödinger's cat, a thought experiment, illustrates this perfectly. A cat in a box can be both alive and dead until observed. It's a stark reminder that reality at the quantum level doesn't behave like our everyday experiences. Interpreting what this means for the nature of reality has led to a variety of interpretations, each with its own implications. The Copenhagen interpretation, one of the most widely accepted, suggests that particles don't have definite properties until they are measured. This view implies that reality is, in some sense, created by our observation. On the other hand, the many-worlds interpretation posits that all possible outcomes of quantum measurements become real in some world or universe. It's a mind-bending idea that suggests reality is a vast, ever-branching multiverse. Then there's the pilot wave theory, which aims to restore determinism by proposing that particles have definite properties guided by a pilot wave. Each interpretation raises profound questions about the nature of reality and our place in it. These interpretations aren't just abstract philosophical musings, they have practical implications. Quantum computing, for instance, relies on the principles of superposition and entanglement, where bits can be in multiple states at once and particles can be instantly correlated over vast distances. This technology promises to revolutionize fields like cryptography, optimization, and drug discovery. Even in our daily lives, technologies like lasers and MRI machines are rooted in quantum mechanics. Yet, the strange behavior of particles at the quantum level doesn't seem to translate to our macroscopic world. Why do we experience a classical reality? This question remains one of the biggest mysteries in physics. The nature of reality is not just a topic for scientists and philosophers. It's something we all grapple with in our daily lives. When you flip a light switch, you expect the light to turn on. When you drop a cup, you expect it to fall. These expectations are based on our classical understanding of reality. But quantum mechanics tells us that at the most fundamental level, reality is far more complex and uncertain. This disconnect raises intriguing questions. How does the quantum world give rise to our classical experience? Is consciousness somehow involved in collapsing the wave function? These are open-ended questions that continue to fuel debate and research. As we delve deeper into the quantum realm, we're not just uncovering the nature of reality, we're also uncovering the limits of our understanding. Realism versus anti-realism. Quantum mechanics, the branch of physics dealing with the smallest particles and their interactions, has always been a hotbed of philosophical debate. At the heart of this debate lies the question of realism versus anti-realism. Realism, in this context, posits that the world exists independently of our observations and that particles have definite properties before measurement. Anti-realism, on the other hand, suggests that particles do not have definite properties until they are measured, and that our observations play a crucial role in shaping reality. This is not just an abstract philosophical musing. It has real implications for how we understand and interact with the world around us. Consider the double-slit experiment, a cornerstone of quantum mechanics. When particles like electrons are fired at a barrier with two slits, they create an interference pattern, as if they are waves. However, if you try to observe which slit each electron passes through, the interference pattern disappears, and the electrons behave like particles. This phenomenon, known as wave-particle duality, challenges our everyday notions of reality. Does the electron exist as a wave or a particle before measurement? Realists might argue that the electron has a definite state, but we are limited in our ability to observe it. Anti-realists, however, might suggest that the electron state is indeterminate until it is measured, and that our act of observation brings its state into existence. This debate is not just confined to the realm of physics. It seeps into our daily lives, and the way we perceive the world. For instance, when you look at a tree, do you believe it exists independently of your observation, or does your observation play a role in its existence? This might seem like a trivial question, but it has profound implications. If you lean towards realism, you believe in an objective reality that exists independently of your perception. If you lean towards anti-realism, you might be more open to the idea that reality is shaped by our perceptions and interactions. This can influence everything from your political beliefs to your personal relationships. Moreover, the realism versus anti-realism debate is not just about philosophy or physics. It is also about the nature of knowledge and truth. If you are a realist, you believe in the possibility of objective truth, something that exists independently of our beliefs or perceptions. This can give you a sense of certainty and stability in a world that often feels uncertain and chaotic. However, if you are an anti-realist, you might be more open to the idea that truth is subjective and shaped by our experiences and interactions. This can make you more adaptable and open-minded, but it can also make you feel less certain about the world around you. So, which one are you? And how does this belief shape your understanding of reality? The role of the observer. Quantum mechanics, the branch of physics dealing with the smallest particles in the universe, has consistently challenged our understanding of reality. At the heart of this challenge lies the role of the observer. In classical physics, the observer is a detached entity, passively recording events. However, quantum mechanics blurs this distinction. The act of observation or measurement can influence the system being observed. This is encapsulated in the famous thought experiment of Schrödinger's cat, where a cat in a box can be both alive and dead until observed. This phenomenon is not just a philosophical musing, but a practical reality in quantum experiments. Electrons, for instance, can exist in multiple states or places at once, a property known as superposition. But the moment you measure their state, they choose one position. It's as if the universe waits for a conscious observer to pick a reality. This observer effect has led to various interpretations of quantum mechanics. The Copenhagen interpretation, one of the most widely accepted, suggests that particles don't have definite properties until they are measured. In this view, the observer plays a crucial role in defining reality. Another interpretation, the many-worlds interpretation, posits that all possible outcomes of quantum measurements become real in some world or universe. Here, the observer is just one of many, each experiencing a different reality. These interpretations raise profound questions. If the observer influences reality, what does that say about the nature of reality itself? Is reality fundamentally subjective? These questions don't just reside in the realm of abstract philosophy. They have practical implications. Quantum computing, for example, relies on the principles of superposition and entanglement, where the role of the observer is crucial. Connecting this to daily life might seem challenging, but consider this. Our perception shapes our reality. Much like the quantum observer, our actions and observations can influence the outcomes we experience. This isn't to say that we live in a solipsistic universe where reality is purely subjective. Rather, it's a reminder that our engagement with the world around us is active, not passive. We don't just passively receive information, we interact with it, and this interaction can change the information itself. Think about decision-making. When you make a choice, you're not just passively selecting an option, you're actively influencing the outcome. This is a macroscopic analogy to the quantum observer effect. It's a reminder that we have agency, that our choices matter, and that we are not mere spectators in the theater of life. Moreover, the role of the observer in quantum mechanics encourages a sense of humility. It reminds us that our understanding of reality is limited and that there are phenomena beyond our current comprehension. This humility can be a powerful tool in daily life, encouraging open-mindedness and a willingness to learn. It also fosters a sense of interconnectedness. If the observer and the observed are not distinct entities, then we are all part of a vast, interconnected web of reality. This interconnectedness can foster empathy and a sense of shared responsibility. In a world often characterized by division and conflict, this is a powerful message. It's a reminder that we are all in this together, that our actions have consequences, and that we have the power to shape our reality. Quantum mechanics and consciousness. Quantum mechanics, the branch of physics dealing with the smallest particles in the universe, has consistently challenged our understanding of reality. At its core, it introduces a realm where particles can exist in multiple states simultaneously, a concept known as superposition. This is famously illustrated by the thought experiment of Schrödinger's cat, which is simultaneously both alive and dead due to being linked to a random quantum event. Such counterintuitive ideas have led to a variety of interpretations, some of which blur the line between the physical world and the role of consciousness. One of the most intriguing interpretations is the von Neumann-Wigner interpretation, which suggests that consciousness plays a crucial role in the collapse of the quantum wave function. In other words, it's not until a conscious observer measures or interacts with a quantum system that the system chooses a definite state. This idea, while controversial, raises profound questions about the nature of reality and our place in it. If consciousness indeed influences quantum states, it implies a deep connection between the mind and the fundamental fabric of the universe. How might this change our understanding of everyday experiences? Could our thoughts and perceptions be more intertwined with the physical world than we ever imagined? Another interpretation, the many-worlds interpretation, posits that all possible outcomes of quantum measurements become real in some world or universe. This means that every decision you make branches off into a new reality. It's a mind-bending concept that challenges our notions of identity and reality. If every possible outcome is realized somewhere, how does that affect our sense of self and our daily choices? Does it make our decisions feel more or less significant? These interpretations, while speculative, encourage us to think deeply about the nature of reality and our role within it. The relationship between quantum mechanics and consciousness also raises practical questions. For instance, could a better understanding of this connection lead to advancements in technology or medicine? Quantum computing, which relies on the principles of superposition and entanglement, is already a rapidly growing field. If consciousness can influence quantum states, might we one day develop technologies that harness this power? Similarly, in medicine, could a deeper understanding of the mind-body connection, informed by quantum principles, lead to new treatments for mental health issues? These are open-ended questions that invite exploration and debate. They remind us that the boundaries between science, philosophy, and everyday life are often more fluid than we think. The hard problem of consciousness. Quantum mechanics, the branch of physics dealing with the smallest particles in the universe, has consistently challenged our understanding of reality. At its core, it introduces a probabilistic view of nature where particles can exist in multiple states simultaneously, a concept known as superposition. This is famously illustrated by the thought experiment of Schrödinger's cat, which is simultaneously both alive and dead due to being linked to a random quantum event. Such counterintuitive ideas have profound implications for our understanding of reality, especially when considering the role of the observer. In quantum mechanics, the act of measurement or observation collapses the wave function, forcing the system into a definite state. This raises intriguing questions about the nature of reality and consciousness. If consciousness plays a role in collapsing the wave function, as some interpretations suggest, it blurs the line between the physical and the mental, challenging the traditional Cartesian dualism of mind and body. The hard problem of consciousness, as coined by philosopher David Chalmers, is the question of why and how we have qualia or subjective experiences. It's not about explaining cognitive functions like memory or learning, but about understanding why there is an inner aspect to our mental states at all. For instance, why does the firing of neurons in the brain give rise to the experience of seeing the color red, rather than just the ability to recognize it? This problem is particularly pertinent when considering quantum mechanics. Some interpretations, like von Neumann-Wigner interpretation, propose that consciousness causes the collapse of the wave function. Others, such as the orchestra-or orchestrated objective reduction theory proposed by Roger Penrose and Stuart Hameroff, suggest that quantum processes in microtubules within brain neurons play a role in consciousness. These ideas, while controversial, highlight the deep connection between quantum mechanics and the nature of reality, including consciousness. In daily life, the implications of these ideas might seem abstract, but they touch on fundamental aspects of human experience. For example, The role of the observer in quantum mechanics can be likened to the way our perception shapes our reality. Just as a quantum system remains in superposition until observed, our experiences are influenced by our attention and interpretation. This is evident in how different people can have vastly different experiences of the same event, depending on their perspective. Moreover, the hard problem of consciousness reminds us that our inner experiences are not just epiphenomena, but are central to our existence. They are what make life meaningful and personal. Understanding consciousness, therefore, is not just an academic pursuit, but a deeply human one. It's about understanding what it means to be alive, to feel, to perceive, and to exist. This is where quantum mechanics and the nature of reality intersect with our everyday lives, inviting us to ponder the profound mysteries of existence. Quantum biology. Quantum biology is a fascinating field that explores how quantum mechanical phenomena influence biological systems. At its core, it's about understanding how the strange rules of quantum mechanics, which govern the behavior of particles at the atomic and subatomic level, play a role in life processes. This isn't just theoretical musing. There's evidence that quantum effects might be crucial in processes like photosynthesis, bird migration, and even our sense of smell. For instance, in photosynthesis, the conversion of light energy into chemical energy occurs with nearly 100% of efficiency, a feat that's difficult to explain without invoking quantum coherence. Similarly, some birds have been found to use quantum entanglement to navigate using the Earth's magnetic field. It's a bit like having a tiny, ultra-precise GPS system inside your head. The interpretations of quantum mechanics add another layer of intrigue to quantum biology. The Copenhagen interpretation, for example, suggests that particles don't have definite properties until they're measured. This raises questions about how biological systems, which are warm and messy, can maintain quantum coherence long enough for these effects to matter. Then there's the many-worlds interpretation, which posits that all possible outcomes of quantum measurements become real in some world or universe. It's mind-bending stuff, but it could have implications for how we understand evolution and adaptation. If every possible mutation becomes real in some universe, does that change how we think about natural selection? Quantum biology also forces us to reconsider our everyday experiences. Take smell, for instance. The prevailing theory is that we detect different smells based on the shape of molecules. But there's evidence that quantum vibrations might also play a role. This could explain why some molecules with similar shapes smell completely different. It's a bit like realizing that your nose is a quantum sensor, picking up on the tiny vibrations of molecules. This isn't just academic curiosity. It could lead to better understanding of diseases like Parkinson's, which is linked to a loss of smell. It's a reminder that the quantum world isn't just out there in the lab. It's a part of our daily lives, shaping our experiences in ways we're only beginning to understand. All of this raises some big, open-ended questions. How do biological systems manage to maintain quantum coherence in the face of noise and warmth? Are there other life processes that rely on quantum effects that we haven't discovered yet? Could understanding quantum biology lead to new technologies, like more efficient solar cells inspired by photosynthesis? It's a bit like standing at the edge of a vast, uncharted territory. The more we learn, the more we realize how much we don't know. But that's the excitement of science, isn't it? It's not just about finding answers, it's about asking better questions. And in the case of quantum biology, those questions might just change how we understand life itself. The holographic principle. The holographic principle is a fascinating concept in theoretical physics that suggests all the information contained within a volume of space can be described by the information on the boundary of that space. This principle emerged from the study of black holes and string theory, challenging our conventional understanding of space, time, and information. It posits that the universe could be a kind of hologram, where the three-dimensional world we perceive is a projection from a two-dimensional boundary. This idea is not just a philosophical musing, but a serious scientific hypothesis with profound implications. Consider the implications of this principle in our daily lives. If the holographic principle is correct, it means that everything we experience, every object, every interaction, is a projection from a lower dimensional reality. This could revolutionize our understanding of reality itself. For instance, it might explain why certain physical laws seem so fundamental and universal. It could also provide a framework for unifying quantum mechanics and general relativity, two pillars of modern physics that currently remain separate. The principle suggests that the information encoding our universe might be stored on a distant, two-dimensional surface, much like a hologram. This idea raises many open-ended questions. If our universe is a hologram, what is the nature of the boundary that encodes it? How does the information on this boundary translate into the three-dimensional world we experience? And perhaps most intriguingly, could this principle help us understand the nature of consciousness? Some theories suggest that consciousness itself might be a holographic projection. This is speculative, but it highlights the profound implications of the holographic principle. It challenges us to think differently about the nature of reality and our place within it. The holographic principle also connects to the concept of emergence in physics. Emergence refers to the way complex systems and patterns arise out of simple rules and interactions. For example, the intricate patterns of a flock of birds or the behavior of a school of fish emerge from the simple rules followed by individual members. In a similar way, the holographic principle suggests that the complex, three-dimensional world we experience might emerge from simpler, two-dimensional rules. This idea is not just abstract. It has practical implications for understanding the fundamental nature of the universe. It could lead to new technologies, new ways of processing information, and even new forms of communication. The holographic principle is a reminder that reality is often stranger and more fascinating than we imagine. The simulation hypothesis. Quantum mechanics, the branch of physics dealing with the smallest particles in the universe, has consistently challenged our understanding of reality. At its core, it introduces concepts like superposition, where particles can exist in multiple states simultaneously, and entanglement, where particles become interconnected and the state of one can instantly affect the other, no matter the distance. These phenomena defy classical physics and our everyday experiences, leading to a plethora of interpretations and theories attempting to make sense of it all. One of the most intriguing and mind-bending interpretations is the simulation hypothesis. The simulation hypothesis posits that all of reality, including the quantum realm, is an artificial simulation, much like a highly advanced computer program. This idea, popularized by philosophers and technologists alike, suggests that what we perceive as reality is actually a constructed experience, created by a highly advanced civilization or entity. It's a concept that blurs the lines between science and philosophy, raising profound questions about the nature of existence. For instance, if we are living in a simulation, how would we know? What would be the telltale signs, and how would they manifest in our daily lives? Consider the pixelation of a low-resolution image. In a simulation, there might be similar limitations or glitches that reveal the artificial nature of reality. Some proponents of the simulation hypothesis point to quantum indeterminacy as a potential sign. The idea is that if reality is a simulation, it might only render details as they are observed, much like how a video game only renders details as the player moves through the environment. This is reminiscent of the quantum phenomenon, where particles don't seem to have definite states until they are measured. It's a fascinating parallel that invites further exploration and debate. Moreover, the simulation hypothesis encourages us to think about the implications of such a reality. If we are indeed living in a simulation, what does that mean for our understanding of consciousness, free will, and the meaning of life? It's a topic that can be both unsettling and liberating. On one hand, it might suggest that our experiences are not as real as we think. On the other hand, it could imply that the boundaries of our reality are only limited by the parameters set by the simulators. This opens up a world of possibilities, from the potential to hack the simulation to the idea that we might one day create our own simulations. It's a thought-provoking concept that challenges us to question our perceptions and consider the broader implications of quantum mechanics and the nature of reality. Quantum mechanics and the arrow of time. Quantum mechanics, the branch of physics dealing with the smallest particles in the universe, has consistently challenged our understanding of reality. One of the most perplexing aspects is its relationship with the arrow of time, the one-way direction in which we perceive time to flow. At the quantum level, time's arrow isn't as straightforward as it is in our everyday experiences. In classical physics, the second law of thermodynamics introduces an arrow of time through the increase of entropy or disorder in a closed system. However, quantum mechanics operates under different rules. Quantum systems can exist in superpositions, where particles can be in multiple states or places at once. This superposition can lead to intriguing phenomena, such as quantum entanglement, where particles become linked and the state of one can instantly affect the state of the other, no matter the distance. This instantaneous connection seems to defy our classical notions of time and causality. The arrow of time in quantum mechanics is further complicated by the measurement problem. When we observe a quantum system, the superposition collapses into a definite state. This act of measurement introduces a subjective element to the arrow of time. Some interpretations, like the Copenhagen interpretation, suggest that the arrow of time is a result of our interaction with the quantum world. Others, like the many-worlds interpretation, propose that all possible outcomes of quantum measurements become real in some world or universe, making the arrow of time a more complex, branching phenomenon. These interpretations raise profound questions. If time's arrow is subjective, how do we reconcile it with our objective, shared experience of time? If all outcomes are realized, how do we make sense of our linear, cause-and-effect reality? Connecting these quantum peculiarities to daily life might seem daunting, but there are intriguing parallels. Consider the act of making a decision. In our everyday lives, decisions seem to have clear causes and effects, following a linear timeline. Yet, at a fundamental level, the process might be more akin to a quantum superposition with multiple potential outcomes. The act of choosing or observing collapses these possibilities into a single reality. This perspective can make everyday choices feel more fluid and less deterministic. It also raises questions about free will and the nature of choice. Are our decisions predetermined, or do they emerge from a quantum soup of possibilities? Similarly, the concept of entanglement can reshape how we view relationships and connections. Just as entangled particles remain connected regardless of distance, our interactions with others might have deeper, more instantaneous connections than we realize. These quantum insights also challenge our understanding of memory and perception. In classical physics, memory is a record of past events, a testament to the arrow of time. But in quantum terms, memory might be more malleable. Some theories suggest that quantum effects could influence our brains, making memory a more dynamic, less reliable process. This could explain why eyewitness accounts often differ or why our memories of events can change over time. It also raises questions about the nature of reality itself. If our perception of time and memory is influenced by quantum effects, how accurate is our understanding of the world? How much of our reality is a construct of our quantum interactions? These questions don't have easy answers, but they invite us to explore the boundaries of our understanding. They remind us that the universe is a complex, interconnected web, where the smallest particles and the largest scales are bound by the same fundamental rules. The interpretation of probabilities. Quantum mechanics, the branch of physics dealing with the smallest particles in the universe, introduces a probabilistic nature to the behavior of these particles. At the heart of this lies the interpretation of probabilities, a concept that diverges significantly from classical physics. In the quantum world, we can't predict with certainty the outcome of an event, like the position or momentum of a particle. Instead, we can only calculate the probability of a particular outcome. This is encapsulated in the Born rule, which states that the probability of a quantum event is given by the square of the amplitude of its probability wave function. It's like rolling a dice, but the dice is influenced by an invisible, ever-changing force. The interpretation of these probabilities has led to various philosophical debates and interpretations. The Copenhagen interpretation, one of the most widely accepted, suggests that particles don't have definite properties until they are measured. It's like saying a spinning coin doesn't have a heads or tails until it lands. This interpretation brings probability into the forefront, as the outcome is inherently uncertain until observed. On the other hand, the many-worlds interpretation posits that all possible outcomes of a quantum measurement become real in some world or universe. It's like every choice you've ever made spawns a new reality. These interpretations raise profound questions about the nature of reality and our role as observers. Connecting this to daily life might seem challenging, but consider this. Uncertainty is a part of our everyday experiences. We can't predict with certainty what will happen tomorrow, just as we can't predict the exact behavior of a quantum particle. We make decisions based on probabilities, like the likelihood of rain affecting our plans or the chance of a particular investment paying off. Even in technology, quantum probabilities are at play. Quantum computers, for instance, use the probabilistic nature of quantum bits or qubits to perform complex calculations much faster than classical computers. They're not just science fiction, they're being developed and tested right now. Yet, the interpretation of these probabilities remains an open-ended question. It's a topic that blurs the line between physics and philosophy. It challenges our understanding of reality and forces us to confront the limits of our knowledge. It's like standing at the edge of a vast, unexplored territory where the rules of the game are still being written. So, the next time you're faced with uncertainty, remember that you're experiencing a fundamental aspect of the universe, one that even the brightest minds are still trying to understand. It's not just about the dice roll, it's about the nature of the dice itself. The future of quantum mechanics. Quantum mechanics, with its counterintuitive principles, has been the bedrock of modern physics for nearly a century. It's a field that's not just about understanding the very small, it's about grappling with the nature of reality itself. The future of quantum mechanics is poised to bring about transformative changes, not just in our understanding of the universe, but also in technology and daily life. One of the most intriguing aspects is the exploration of different interpretations of quantum mechanics. The Copenhagen interpretation, many-worlds interpretation, and objective collapse theories each offer unique perspectives on what's happening at the quantum level. These interpretations raise profound questions. Is the universe fundamentally probabilistic? Do all possible outcomes of quantum events actually occur in some branch of reality? Or is there a mechanism that causes quantum superpositions to collapse into definite states? The implications of these interpretations extend far beyond academic debates. They touch on the very fabric of reality and could influence how we develop future technologies. Quantum computing, for instance, relies on the principles of superposition and entanglement. A deeper understanding of these phenomena could lead to breakthroughs in computing power, cryptography, and even artificial intelligence. Imagine a world where quantum computers can solve problems that are currently intractable, revolutionizing fields like drug discovery, climate modeling, and financial forecasting. The potential is vast, but so are the challenges. How do we reconcile the strange behavior of quantum particles with our classical understanding of the world? Can we harness these quantum effects in practical applications without losing coherence? Moreover, the future of quantum mechanics is intertwined with our daily lives in ways we might not yet fully appreciate. Quantum sensors, for example, could revolutionize medical imaging, enabling earlier detection of diseases. Quantum communication networks could provide ultra-secure channels for transmitting information. These advancements are not just about pushing the boundaries of science. They're about enhancing our quality of life. Yet, with these opportunities come ethical and philosophical questions. How do we ensure that quantum technologies are used responsibly? What are the implications for privacy and security in a quantum-connected world? These are open-ended questions that will shape the future of quantum mechanics and its impact on society. As we delve deeper into the quantum realm, we're also confronting the limits of our current understanding. The quest for a unified theory that reconciles quantum mechanics with general relativity is one of the most pressing challenges in physics. String theory, loop quantum gravity, and other approaches offer tantalizing glimpses of a deeper reality. But the path forward is fraught with uncertainty. What if our current frameworks are incomplete? What if there are aspects of reality that we haven't even begun to imagine? The future of quantum mechanics is not just about answering these questions. It's about asking them in the first place. It's about embracing the mystery and the wonder of a universe that is far stranger and more beautiful than we ever thought possible. As we wrap up our journey through the mind-bending world of quantum mechanics, let's take a moment to recap the key points that have danced across the quantum stage. We've seen how particles can be in multiple places at once, how they can be entangled across vast distances, and how observation itself can change the outcomes we see. These aren't just abstract ideas. They're the very fabric of reality, weaving a tapestry far stranger than anything we encounter in our day-to-day lives. Now, you might be wondering, how does this affect me? Well, quantum mechanics isn't just about tiny particles in labs. It's about the nature of reality itself, and that's something that touches every aspect of our lives. The next time you're staring at the stars, or feeling the warmth of the sun, or even just clicking a button on your phone, remember that beneath the surface, the quantum world is buzzing with activity, shaping the universe in ways we're only beginning to understand. So, where do we go from here? The interpretations we've explored, Copenhagen, many worlds, pilot wave, each offer a different lens through which to view reality. Which one resonates with you? Do you find comfort in the simplicity of Copenhagen, or do you prefer the boundless possibilities of many worlds? Maybe you're drawn to the deterministic path of pilot wave. The beauty of science is that it's a journey, not a destination. There's always more to explore, more to question, and more to discover. As we continue to unravel the mysteries of quantum mechanics, we invite you to join us on this adventure. Subscribe to our channel for more deep dives into the nature of reality, and don't forget to hit the bell icon so you never miss an upload. And remember, the next time you're faced with a decision or a moment of uncertainty, think about the quantum world. Maybe, just maybe, the answer lies in the strange and wonderful realm of the very small. Until next time, keep questioning, keep exploring, and most importantly, keep wondering. The universe is a strange and beautiful place, and it's waiting for you to discover its secrets.